Look up on a clear night, and the universe seems entirely peaceful. The stars look like quiet, distant pinpricks of light. But that stillness is a lie. Hiding in the dark are volatile giants. The heaviest stars in our galaxy are ticking time bombs. They spend millions of years burning through their fuel, building toward an inevitable, explosive death. This diagram shows the core problem with these explosions. In everyday life, you usually see or hear a warning before a disaster strikes. But here, the lethal radiation and the visible light telling you it happened travel at the exact same speed, the speed of light. A standard star death 3,000 light-years away would be a harmless light show. But if that same energy is focused into a narrow beam, it can cross the entire galaxy with its lethality intact. Survival in this environment is often a matter of simple geometry. Avoid standing in the direct line of sight of a dying giant. To understand how a star builds this weapon, we have to look inside it. Deep in the core, a massive star survives on a delicate balance. Inward crushing gravity fights against the outward push of nuclear fusion. Eventually, the fuel runs out. The nuclear fires fade, the outward pressure drops, and gravity finally wins a battle it has been fighting for millions of years. The breaking point happens in an instant. The star builds up a heavy iron core that suddenly becomes too massive to support its own weight, triggering a catastrophic collapse. In just milliseconds, an inner core the size of Earth is crushed down to a microscopic point. That violent compression leaves a newly born black hole right at the heart of the dying star. Because this happens so fast, the outer layers of the star don't realize the core is gone. Millions of trillions of tons of superheated gas continue to free fall toward the center. The star's own immense mass has created a gravity trap so extreme that it sets the stage for the most powerful cannon in the universe. All that star stuff plunging into the black hole gets stuck in a cosmic traffic jam. It forms an accretion disk, a superheated, flat ring of gas spinning at a fraction of the speed of light. This diagram shows how the disk acts like an engine. As it spins, it grabs and violently twists the black hole's magnetic fields. They become a massive particle accelerator, pinching together to grab infalling matter and firing it outward. This acceleration process converts raw gravitational energy into two concentrated, piercing jets of pure gamma radiation, the highest energy form of light in existence. The gravitational collapse effectively creates a highly efficient mechanism that directs the star's final energy into a single focused point. Deep inside the star, these newly formed gamma-ray jets act like cosmic drill bits, pushing fiercely against the collapsing outer layers trying to fall in. The beams face incredible resistance. They have to punch through millions of miles of dense stellar plasma. In the exact fraction of a second the beams breach the star's surface, they outshine the rest of the galaxy combined. Once the beams clear the star's surface, the energy is no longer a localized event. It is a gamma-ray burst. The burst leaves its host galaxy and enters the interstellar vacuum. Because it is made of pure light, it travels at the speed limit of the universe. The physics of its path are what make it so dangerous. A normal explosion scatters its energy in all directions, losing power fast. This beam is tightly focused, allowing it to maintain its intensity over vast distances. Look at this graph comparing a spherical explosion to a focused beam. While a normal explosion's energy decays almost immediately, the burst's line stays nearly flat. Even after millions of years, it retains enough power to incinerate a planet's atmosphere. And it does this in absolute silence. Because the burst itself is traveling at light speed, no precursor signal can ever outrun it to warn a target. It acts as an eternal cosmic sniper bullet, holding on to its lethal power across unfathomable expanses of space until it hits something. So, what if a gamma-ray burst intersected directly with Earth's orbit today? The immediate reaction happens high above our heads. The gamma radiation would cook the ozone layer, stripping away our primary defense against the sun. This diagram shows the mechanism of destruction. Without the ozone layer, unfiltered solar radiation and cosmic rays flood the surface below, destroying the food chain and triggering a rapid mass extinction event. You don't need to lose sleep over it. The statistical probability of a burst aligning perfectly with our tiny planet in the endless void of space is incredibly low. The universe is filled with these silent, light-speed snipers. The fact that life has had the billion-year window necessary to evolve and eventually study them is a stroke of statistical luck.